Alright, first things first, let's install the packages that we need using pip install. For actually connecting to the Earth Engine, we'll need to install Earth Engine API package, followed by GEmap for actually fetching the data, and then we need a couple of packages, volume raster and NumPy for data wrangling, and finally matplotlib for creating a map. Once you have all the packages installed, we're going to go ahead and import them one by one. The first one will be, of course, the Earth Engine package EE. Then we will import volume, and after that we're going to also be importing GEmap. Specifically, from GEmap, we'll be actually fetching the one that allows us to create easily an interactive map, so that we can actually then show this Google Earth Engine data. And then, of course, NumPy for data wrangling and Areao to work with actual raster files. And finally, we're going to be importing matplotlib, of course, the plot function from it, so that we can actually create our map in this session. All right, we are still warming up. We first of all installed packages, and then we loaded them. Then I showed you how you can create your Earth Engine project if you don't already have one. Now what we're going to do is set up our environment to work properly. And that means creating a single file and a single path where we will be storing all those geotiffs, all those maps. So this folder is going to be called EE_outputs. Of course, you can name it a different way if you want. Why we are doing this? Because we want to have a single place where, at any time we can go and, search for these outputs without, guessing where it is. And then once this is done, the next thing that you need to do is you need to actually set your Earth Engine credentials, of course, so that we will be then able in the later stages fetch the data. So what I'm doing here, I'm setting this as like just a global environment one, so EE project, and then this is the name of my project. Of course, you should put yours over there. And once you actually add these credentials, then we will be using them later on to fetch the Earth Engine data. So one very important thing is that apart from your Gmail account, which is associated then with also your Google Cloud account, you also need to have a project created. I'm going to now show you on an example how you can do that. So you first of all need to go to your browser and then to this page, which is console.cloud.google.com. And then if you already have here your Gmail account, that's fine. Click just on this select project and then new project. Within the new project, you just need to name it here. You don't need to choose any organization, so I'm just going to put here some random name. And once you're done with that, you need to click here on create, which is then going to actually create your project. Once that is done, this project will be enlisted there, so it's going to take a while, a few seconds to create it. And now it's created. You can click on select project, and over here you can then find some information about your project as well. So now we're going to be using those credentials that you defined in the previous step over here, so that you can actually authenticate and initialize your Earth Engine session from Python. So what I'm doing here is, first of all, I'm using the credentials to initialize, and I'm here providing the project name. And then if this initialization does not really happen, I first need to then authenticate. So what I'm going to do here, if this does not happen, I'm first going to then authenticate. So that's why I'm writing this here. And once this is authenticated, then you are good to go. So remember this, you need to pass here what you previously defined, so the name of your project, and this is then help us first of all authenticate and then initialize, or initialize first if you already authenticated. But the main thing is that you already have your project defined in Google Earth Engine, so that we can start with this next step. And then as a very last step in this whole part, we're just going to verify that the connection between the server and the client actually works by putting or inserting this very small test where 1 + 2 should be equal 3. So once you actually write this and then you run this, you should be able to get as an output 3 once you actually print this. So that's the whole thing here. And the message here is just like connectivity test. I'm just writing here so that it's human readable and understandable. But essentially, you have to see number 3 here is everything is correct. As you can see here, I got that result. In this tutorial, we'll be fetching the data for the Viva Lake. So you can go actually to this bboxfinder.com and you can select either this one, or you can go for your own bounding box of interest. But what you will do next is simply in this lower left corner, simply we're going to be copying these values next to this box. So I just pasted here these bounding box coordinates, and what we're going to do next is we're going to use them to create our bounding box, which is then going to be passed to Google Earth Engine. So I'm just defining here the minimum latitude and longitude values, and once that is done, we actually need to create a polygon. So a geometry, from a geometry model there is a polygon attribute, and over here we just need to pass in a certain order. So we need to actually create here several pairs. So first of all, minimum longitude and minimum latitude, followed by minimum longitude and maximum latitude, and then two more. I'm just going to actually copy here so it's easier and just change. So we have the maximum longitude, maximum latitude, and then the maximum longitude and the minimum latitude. We're finally ready to fetch the data. So in this section 4, we are going to go and fetch the annual satellite embeddings from Google for 2024. So what we're going to do here is we're going to pull the 2024 annual satellite embeddings. Then we're going to mosaic them into a one image. Then we're going to clip them into this area of interest and then cast to a float so that each pixel has a 64-dimensional descriptor. So this is exactly what I'm doing here, step by step. And of course, because we are interested here in this specific collection, we need to define. So it's Google Satellite Embedding version 1 annual. This is the exact path that you should also be using. Because we're interested in 2024, we're filtering everything between 1st of January 24 and 1st of January 25. And then, as I said, we're simply mosaicing. So putting this together and then clipping, or basically cutting this, clipping this by the region that we defined. And finally, just casting this into a float. As we define the data we need, we're going to go ahead and prepare the sample pixels for training. So we're going to define actually here 1000 samples, randomly assigned. And then we're gonna, what we're gonna do next is we're gonna sample them and define some values. So we're gonna be sampling them for this region. We're going to be using the scale of 10 meters. Of course, we're passing here the number of these samples. We're setting the seed for reproducibility, and then we're also setting that we don't want geometries here. So why we're actually doing this? We are training actually on a small representative subset because it's fast and it avoids streaming the full image. And the trained model can then be applied server-side over the full area of interest that we defined. Now we're going to go ahead and define our k-means clustering helper because we want to do k-means clustering. So what this function will be doing is it's going to train k-means model with this 1000 number of clusters that we defined. Then it's going to assign each cluster a label per pixel. So clustered underscore k5 is going to be the 5 class results, clustered underscore k3 is going to be 3 class result, and clustered k10 is going to be the 10 class result. That's exactly what we are doing here. And then the next question is why we're doing this. Well, this actually let us reuse the same training and the application logic for multiple k values. In essence, you could create then this for any other number of k values. So 3, 5, and 10 is just for example here. And this is actually again going to help us compare segmentation granularity. So this is exactly what we are doing here. And what is actually important here is just to remember that to use exactly these functions here. So these functions are the ones that are going to be executed on the Google Earth Engine side, so on that server side, and there is nothing that we need to do locally. So that's very, very convenient. And we're ready to create our interactive map. But what would be a map without a nice colorblind friendly palette? So I use this Kelly22, which actually comes from my previous art tutorial, and I had to manually define it here. You can actually pass some other one, it doesn't really matter. I just like this one. And we're not going to be using all the values from this one, only 10, but that's the thing. And this is what we're actually defining here. So what we're doing here, we're going to be creating here an interactive map using Folium, and this is going to be our palette. So this is why we're defining here map as M, and then we're calling from GE Folium. We're calling the map module and then defining here that we want to actually define, to zoom this into our region of interest. And the zoom level is going to be 13. And this is exactly what we're doing. So it's a very short, a very nice one. And we can also here add a base map that we're interested in. You can add street view layer, for example. I opted for the satellite layer. And you can also go for some other things. For example, you can add an initial layer here to your map, and you know, this additional layer is actually going to be your clustering results, or k-means clustering results. So this is what I'm doing. I'm doing for the K5, so the one that has 5 clusters. I'm adding this as a layer, and then I'm going to define here as well a title, which is going to be K5 clusters. And of course, you need to pass here this viz that we defined. The viz is basically the one that adds these palettes. Now you have here also the bounds, so it needs to fit to the bounds that we have, and the bounds are going to be the bounds of the bounding box that we have. So this is what we're doing, and then we're also going to define here what is going to be the map path, where it's going to be saved and how is it going to be named. Basically what I'm doing here is I'm defining here this as an HTML, so not only you will be able to kind of open this, but you can do anything, or literally anything you want with this one. So after this is done, what I'm going to do here, I'm going to also go ahead and save this HTML file. So again, you will have then this locally, this file, and you can do whatever you want with it. All right, this is it. I just opened that HTML file that we saved, and as you can see in the background there is a satellite imagery, and over it overlaid with this lake, so the K5 embeddings. You can also do it for K10. You can also do it for any area you want, just you need to define the area of interest. But this is not all. I'm also going to show you how you can export these images locally for each of these clusters, so that then you can actually play with these raster files and create your own maps the way you want. And this is why we are defining here this function, which is called export cluster local, which accepts actually 2 arguments here. One is a k, which is the number of k-means clusters, and the other one is path. So what we are essentially going to just do here, we're not going to go ahead and use this get clusters. We're going to convert it to integer, and then I'm going to clip the region of interest. So essentially we are again doing the same operation, but this time what we're going to do is we're going to save this again locally as TIFF images. So that's why I'm using this TIFF, and then defining here the directory where they're going to be saved. And then I'm going to using simply from gmap a very convenient function ee export image, which then defines what exactly we want to export and in what scale. So 10 meters, what is our area of interest, so that would be this region that we previously defined. And then of course whether we want files per band or not. So this is something that we skipped. And then finally we just return these TIFF images. So that would basically be the function. Then we can call this function. So for each of the cluster values we can do this, and in our case that would be 3, 5, and 10. Once we define these cluster values, what we do is then in this cluster path we simply use this export cluster local function. So we call it, and then for each of these Ks that we previously defined, we want to download them locally, of course. So we are just putting here this into the loop, and then if you did everything right, you should be able to see this now downloading this 1, 2, and then finally 3 files. So all of them are now downloaded locally. Easy peasy. The next part is using these local raster files to create our map, which is going to show each of these clusters, K3, K5, and K10. So we're going to first of all go ahead and define a function which is going to help us actually read this single band TIFF files one by one. And here we call to rescue rasterio, which is first going to help us open these files. So we're going to read those files into our current session. And then here we're going to also define the specific extent for which we want to get this. So we're going to be defining here our bounds. So a left bound, so that would be west, right, which would be east, and then after that bottom, which is south, and top, which is north. So this function just kind of sets some parameters on how we can, load now these. Also here you can go ahead and transform in the appropriate coordinates reference system. So we also define it here that one. And then at the end we just return these different segments. So this file, the extent, transform, and then the coordinates reference system. We will be needing this. So in the next step, as we now load into this session all these cluster TIFFs, that we can just apply this convenient function, this helper read single band. And this is exactly what we're doing now. So we're doing this for first of all the one that has 5 clusters, and as you can see we're here reading the one which is clusters underscore K5. We're going to be now doing the same for 3 and for 10. So you might be wondering why we're doing in this order. That is because this is how they were downloaded, and this is what we are just following. So over here, you just replace these thingies, and then this function is going to help you to that. So as we define now that helper that's going to help us load, of course, those TIFF files, it's time to create our plot. And here we're going to be using matplotlib and specifically the function subplots to help us actually put together all these 3 maps into a single plot. And that's exactly what we're doing. So what we're doing here, we're saying we have 3 plots, so 1 to 3, and then we are defining here the dimensions of this. So we're going to have a bit of a wider width, so 12, and a bit of a shorter height, which is 4. Then we are creating here a loop. A loop is basically because we have these 3 files. So essentially for each of them, we want to load the TIFF file itself, we want to define the title, and we want to have the appropriate K, which is K corresponding to the cluster itself. So this is why we are defining here, and we are defining in which order we want this to appear. So despite having downloaded in a very different order, we want actually these maps to appear as 3, 5, and 10. Then after this is done, we're going to import some more modules here from matplotlib, which are going to help us deal with the scaly colors that we have and to be able to actually show them properly, so the custom palette. And then also we're going to here define the boundaries, of course, our plot, so that everything actually fits into the screen. So we are actually here readjusting a bit the left and the right side and also the middle. That's basically it what we are doing in this part. And once this is done, what we're going to do next is what is very important is we're not going to have interpolation here between values. So we're going to go ahead and have discrete values. So that's something also to keep in mind. Right, and then we're going to set the title here of our plots, which is going to be just title for each of those clusters. For the X and Y axis labels and also ticks, we're just going to keep them empty. So we are putting, that's why we're putting that here. If you, however, prefer coordinates, you can actually leave this here. And then we're going to actually export this our panel map or panel image to this directory of ours, and we're just going to call this image clusters underscore panel png. And then as a final step, we are going to use savefig from matplotlib to save it. Here I'm defining dots per inches, so 300. You can increase if you want, crisp per image. And also I'm here defining how tight I want it to be saved. And finally here, I'm simply closing everything. So when this is done in literally no time. So if you did everything like I did here, you should be able to see in the next step your image. So here is the final panel map, starting with K3, then going to K5 and K10 means, and using the Kelly palette. Alright, so welcome to the second part. In this section, we will be doing the change detection analysis, and for that we'll be exporting this time directly to our local drive those TIFF files that we need. So we actually need 2 embeddings here. One is going to be for 2018, so that's kind of our base year, and then 2024, so we're going to be comparing 2018 to 2024. Now to do that, we're going to be first of all defining a function to fetch the embeddings data. We're going to call it getSatelliteEmbeddings. It's going to accept 2 arguments. These are Y0 and Y1. Now what do they mean? Y0 is the starting year when you're fetching Google Satellite Embeddings, and Y1 is the ending year. Because we are here doing, for example, for 2018, we would need to start then from 2018, 1st of January until 2019, 1st of January. And the same goes for 2024. If we want the data for 2024, we need 1st of January 2024 until 1st of January 2025. So this function, this helper here, is going to help us do that. So that's why here we're filtering by date Y0 and Y1, and then first 1 and 1, meaning January the 1st. We're of course going to mosaic that embedding we get. We're going to clip by the area of interest we have, and then we're going to convert it into a float. And then once this is done, we're going to simply apply this to our years of interest. As we said, 2018, 2019, so that would be the range for 2018, and 2024 and 2025, that's going to be for the embeddings for 2024. So now we're going to go ahead and compute the mean absolute difference, or as I call it here, MAD. So what it does is computes the average absolute per band difference across these 64 different vectors, dimensions, yielding a single band change magnitude map, which then we'll export as GeoTIFF. And the reason why we're doing this is we want to highlight how much the embeddings changed overall, so magnitude. But with this, we're not going to be able to answer whether it's increase or decrease. So that's the whole point of this. So now what we're doing here is we are subtracting here from 2024, 2028, and then we're converting to absolute values and computing the average using this reducer function from the EE module. And after that, as you can see, we are exporting this to this TIFF, and this TIFF is going to be called mean absolute difference TIFF. So if you did everything well, you should be able now to see that it's downloading this data, and that this is completed, and that the data is downloaded, as you can see, to our EE outputs under this name that we defined, which is mean absolute difference. And one thing also important, we are again using the same scale, so we're using 10 meters here, and we're using for our region or area of interest. Then, using these geotips, we're going to go ahead and compute cosine similarity across these 64 dimensions. So the first thing we'll do here is convert to array both embeddings 2018 and 2024, so that we can then use that in our analysis. Okay, so once this is done, what we're going to do next is we're going to compute Euclidean norms or magnitudes of each vector, which is element-wise squaring of each vector's components. So this array reduce is going to sum the squares across features and then extract the scalar. And then the square root is going to simply just take the square root of this one. So that's basically it. Now, why we are doing it? We're doing this because cosine similarity divides the dot product, which we're going to define in the next step, by the product of its length. So we need both the magnitudes to normalize the dot product and make the measure scale invariant. But in this step, I actually skipped the dot product calculation. That's something we should do first. So we are going to do this for both of the A and B. In this follow-up step, we're going to guard against divide by zero, compute cosine, clamp, and then mask it. So the first one basically just helps us, multiply the denominator A and B. Then dot point divide. Then what it does is a row cosine value per pixel. And then clamp is the one that basically normalizes its values between -1 and 1, so they don't go over the board. And the final one is the update mask, which masks out pixels where the denominator is 0. So those are non-informative, unsafe to divide. And one thing that I should have done at the very beginning is defining this dot product, which is first of all, A multiply B is the element-wise multiplying the two arrays at each pixel. And then we have this command array reduce, where we are actually summing along axis 0, so the band feature axis, and then this collapses the 64 dimensions into an array to one element, containing this A and B multiplication. And then the final one is array get 0, which extracts that scalar from the one element array, so it becomes a scalar EEE image band with the dot product value at each pixel that we then put into the next row, where we actually then calculate these, or actually we just make sure that the ranges are between -1 and 1. Okay, so in this previous part, which was a bit complicated, what we essentially did with computed a numerically safe per pixel cosine similarity between the two high dimensional embedding vectors, so that we can actually map the magnitude and directional change between 2018 and 2024. Now, in this remaining part, we are just going to export then these images, and this is what I'm doing here, and defining actually the directory where they're going to be saved, and then also the name. So we're going to do this cosine 2018-2024. This is going to be a TIFF file, and then we're going to be using this gmap for exporting this image once again. And providing here what exactly we want to export and how we want to export. We want it again to be 10 meter scale, and then we also want it simply for our region of interest over here. And then once this is done and you start actually running this, you should be able to see that it's downloading the data, and then at the end the data should be downloaded here to your a directory with this name of choice, and of course it needs to be a TIFF file. And then we're going to go ahead and define a helper for rendering single band rasters with the color bar, and then plots our MAD and Cosine layers to actually high DPI PNGs. And we are doing this because Earth Engine computes and exports the rasters, but local matplotlib gives actually full control of the publication quality reproducible figures. This is why we're doing that. Now back to the code itself. We're here defining this helper. It's going to be called plot single band TIFF, and it's going to accept several arguments. So it's going to have the TIFF path, it's going to have a title, and then for the color map, we're going to be using the magma path, which is recognized, of course, in matplotlib. We're not going to have this Veen, positional argument here. So we're just going to declare them as none, and then after that we can actually put what we want, and of course where we want to save this. So again, we call rasterio, and this is going to help us load, of course, the TIFF files. We do pretty much the same what we did in the previous steps when we were doing this just for 2024. So we define here what is the actual attribute, or what is the image. So we read that one. Then the extent, of course, we defined what is the bounding box, and then we're gonna go and get this figure and define the figure size. This one is going to have a bit different dimensions, so 7.5 and 6 inches. And then we're going to apply to that TIFF file our color map, which is magma, and here we're going to give to the user to define this minimum and maximum zoom. And then again, I'm going to get rid of the X and Y title and ticks and also labels. If you want to keep the coordinates here, you can do that. It's not a problem. After that, we're going to apply our color bar, which is going to be, in this case, a continuous one. Just here, one more guardrail. If the out file or output file is none, is not none, in other words, it's not none, then we can go ahead and save this as a local one. Here I'm using a bit higher DPI, so to have a higher quality image for the publication, for example, 600, and after that what I'm doing is just closing this figure generation, and that's about it. In the next step, we're just going to check what we produced. If you run everything well, you should be able to see two maps. First of all, mean absolute difference one, using the magma palette, where the magnitude is increasing with the numbers increasing, and the color palette here is inverted, meaning the higher values are going to be lighter, just to kind of show this here. You can see here actually lake doesn't really change much, so it's very, very dark. And the second map, which is the map of cosine similarity between 2018 and 2024, where lower values mean more change, and lower values here are actually those leaning towards -1. So here we actually see a less clear pattern, but the one that points actually to the actual change. Again, this is just about the magnitude. It doesn't tell us about the direction, whether it's increase or decrease in a certain length cover class.